on the center manifold, and equation 100 gives a PDE for the fast, stable modes 0 $.
The core idea of center manifold reduction is that the slow dynamics of alpha dictate the long-term behavior, right? We need to find the equation for alpha.
Correct. Subsection 3.1.1 focuses on these dynamics. The center manifold theorem says the stable modes are enslaved to the slow modes, meaning Zell can be written as a function all the amplitudes. Alpha, AQ103. Substituting this back into the equation for alpha gives the closed amplitude equation. Crucially, the O2 symmetry imposes strong constraints on the form of this equation. O2 symmetry dictates that the evolution equation must respect rotations and reflections. This forces the amplitude equation to take the specific form a d curl p sigma, EQ108, where sigma alpha 2 is the only rotationally invariant combination of alpha and alpha. P sigma is some complex function initially.
So the rate of change of alpha is proportional to alpha itself, times a factor that only depends on the magnitude squared, alpha 2, 2. Expanding this near alpha dollar gives the standard form in equation 109.
Precisely. Equation 109 is alpha lambda plus p sigma plus dos alpha dot equals alpha times the quantity lambda plus p sub sigma of 0 times magnitude alpha squared plus higher order terms. Here, lambda is the linear growth rate, proportional to L2. The coefficient sigma is the crucial cubic coefficient. Its real part determines the stability and direction of the bifurcation.
Okay, so the goal is to calculate this coefficient sigma. Subsection 3.1.2 tackles this. It seems to involve finding the function alpha that describes the stable modes.
Yes, specifically we need the quadratic terms in dollars. The nonlinear term in the original equation contains terms quadratic in the critical modes, like alpha 2. These quadratic terms act as a source or forcing term for the stable modes Zevel. The stable modes respond linearly to this forcing, resulting in several of the dollars being quadratically dependent on alpha and alpha. We need to calculate this response.
The calculation focuses on the opal2 component of dollars, called H2 dollars, YL2.
Because the quadratic nonlinearity involves terms like alpha psi plus alpha su 2. Since Joy contains alpha theta, the square will contain terms like alpha psi and L the other dollar. The LPM of the dollar contains delta theta. It turns out this opal2 response is critical for calculating the cubic term sigma back in the alpha equation.
Okay, so we need to solve for the 2A2 part of the stable manifold response to each dollar, which is done in equation 131. Plugging this back into the projection formulas yields the final expression for the cubic coefficient Talus sigma in equation 132.
Right. Equation 132 is a to the pi to 0, n to 1. Only need to make a 0 I2d. P sub sigma of 0 equals minus pi squared k cubed over 2 times lambda prime sub 1 of 0 times the integral from minus infinity to infinity of d omega g of omega over omega minus 0 minus id squared times omega minus 0 minus I2d. This looks complicated, but it's an explicit formula. The O2 symmetry guarantees that even though the integrand is complex, the final result for PCO log must be real.
Okay, we have a formula for the cubic coefficient. Does that cover subsection 3.1.2?
Yes, the derivation of sigma. Now 3.1.3 applies it to the bimodal example.
Subsection 3.1.3 evaluates formula 132 for the 2 Lorentzian distribution, EQ85, along the steady-state bifurcation curve, KKC. The result, EQ133, gives sigma 0 logs in terms of the model parameters, AKC, epsilon, d, omega do. What does the sign tell us?
The sign of sigma determines the bifurcation type. The calculation shows the sign depends on the term omega 2, omega 2, 2, where omega is related to diodo as napson. If comega omega peaks are close together, sigma is negative, peaks are far apart, sigma is positive.
And what does negative versus positive sigma mean for stability?
If p sigma, the cubic term stabilizes the growth. This corresponds to a supercritical bifurcation. The synchronized state emerges smoothly for phi 2u and is stable. If p sigma, the cubic term is destabilizing. This is a subcritical bifurcation. The synchronized state that emerges is unstable, and the transition is likely to be abrupt or hysteretic.
So just by changing the separation megadol of the peaks in the frequency distribution, the nature of the synchronization onset changes from smooth and stable to abrupt and unstable.
Exactly. The shape of omega dictates the outcome.
Okay, that covers the bimodal example result. Now, subsection 3.1.4 looks at the dollar-to-dollar limit again.
Right, the zero noise limit. This revisits the Vlasov contrast. As dollars to dollars, the denominators in the integral for sigma d EQ132 approach the real axis, causing singularities. If this was Vlasov-Poisson, the coefficient would typically diverge.
But here,
Crawford shows using complex analysis techniques, Plemmel formulas, analytic continuation, that these singularities effectively cancel out or can be handled properly, resulting in a finite value for sigma, even as dillar to dollars. The result is given approximately in equation 139.
Equation 139, $50 0 0 0 do 0 do O fashion 2 $0.
Equation delivered today, 0. For typical smooth unimodal-like distributions, the second derivative is negative and the integral term is positive, making sigma negative overall.
Yes. This predicts that for many reasonable frequency distributions, the steady-state bifurcation should be supercritical in the low noise limit. This confirms the robustness of the analysis compared to Vlasov. Okay, the Vlasov contrast holds for the nonlinear coefficient too. Finally, 3.1.5 briefly mentions perturbing the symmetry. If we break reflection symmetry, moving from O2 to just SO2,
Then the real eigenvalue, lambda dollar, typically splits into a complex conjugate pair near the imaginary axis. The steady-state bifurcation is destroyed and replaced by a Hopf bifurcation, leading to traveling waves instead of a stationary synchronized state. Symmetry breaking drastically changes the outcome.
Okay, let's do a check on the steady-state section 3.1. We derived the amplitude equation, EQ109, focused on the cubic coefficient sigma, calculated at EQ132, saw how its sign determines supersubcriticality in the bimodal example based on omega dollars, confirmed finiteness is liter to dollar, it's less soft contrast, and noted how breaking symmetry leads to waves. Have we missed any key connections or implications?
No, I think we've thoroughly unpacked the steady-state bifurcation. We understand its description via sigma and its dependence on Beiga and, importantly, its well-behaved nature in the low noise limit. The next logical step is applying the same center manifold machinery to the complex eigenvalue case, the Hopf bifurcation.
Right, subsection 3.2. Hopf bifurcation. This is where the main correction happens. Hashtag tag 3.2 Hopf bifurcation.
We're now near Kamor, where a simple, complex eigenvalue lambda complificable crosses the imaginary axis. As established rigorously in section 2 due to O2 symmetry, this eigenvalue is multiplicity 2. The center manifold is four-dimensional.
Spanned by the eigenvector psi, kappa eigenvalue lambda, and their conjugate psi for eigenvalue lambda. We need amplitudes for both eights and kappa phi. Let's call them alpha and butterfall.
Yeah, exactly. Alpha t approx. Alpha t is the amplitude of the mode related by reflection, the one BNS neglected.
Equations 141, 48 set up the decomposition into these critical modes, alpha, beta, and the stable transverse modes, dollar. Section 3.2.1 focuses on the dynamics on this 4D center manifold. Again, the stable modes, psi dollars, are assumed to be a function dollar of the amplitudes, EQ 149. This leads to coupled amplitude equations for alpha and alpha dollars, EQ 150, 151. How does O2 symmetry constrain these?
The symmetry operations act on the amplitudes. Rotation by alpha data transforms them as alpha, beta alpha. E alpha beta equals e to the minus I phi alpha, e to the I phi beta. Reflection swaps them. Kappa na beta alpha, kappa alpha beta equals beta.
These transformations, plus an additional phase shift symmetry inherent in the problem, severely restrict the form of the cubic terms in the amplitude equations. After removing some terms via coordinate changes, normal form theory, the system reduces to the standard O2 Hopf normal form equation 165.
Right. The dynamics depend only on two real invariant quantities. $1 plus beta 202 total intensity, and delta beta 2 alpha 2 difference in intensity between the reflected modes.
This leads to simplified amplitude equations for the real magnitudes 6 beta dollar and 6 beta dollar is 6 beta beta, given in equations 168, 169, and 10. These equations are governed by just two crucial real cubic coefficients called PAMA by $1 plus P by 1 12 plus P0 by 12 plus P0 by 12 plus P0 by 12. The fate of the system which wave pattern emerges and whether it's stable depends entirely on the signs and relative magnitudes of $2 and 2.
And this two-dimensional system predicts two main types of solutions, summarized in Table 1. Yes. First, traveling waves, TW. These correspond to solutions where one amplitude is 0, either 6TW or $2 xTW. Only one of the rotational modes, alpha or beta, is excited. Physically, this is the single circulating clump.
Second, standing waves, SW. These occur when both amplitudes are equal and non-zero, SXSW, XSW. Both the original mode and its reflection are equally excited. Physically, this is the two counter-propagating clumps. The frequency of oscillation omega near criticality is given by equation 170. Okay, so the O2 normal form naturally predicts both TW and SW solutions. Their existence and stability depend on one uncertain. Subsection 3.2.2 explains how to calculate these coefficients.
Similar to the steady-state case, it involves calculating the quadratic response of the stable modes to the forcing from the critical modes. Here, because we have alpha and beta, the quadratic forcing is more complex, EQ179, and we need to calculate 3 different components of the delta-2 response, denoted as Suchidano 1, Torchidano 1, 0, 1, 5, but
Once these are found, equations 177, 178 give the final expressions for Pew dealer and $3 in terms of integrals involving these 22 components and the eigenvector subjoints. And crucially, the paper reemphasizes the Vlasov contrast.
yes, it confirms that, unlike in Vlasov theory, where Hopf coefficients often diverge, like d3 are expected to remain finite as Dale to dollars. This means stable oscillations are predicted even in the absence of noise, a key physical difference.
Okay, we have the formulas for Pew dollars. Let's see what happens in the bimodal example, subsection 3.2.3.
Applying these formulas to the 2 Lorentzian population at the Hopf boundary Corkera, Crawford determines the signs of the coefficients. By inspection of the integrals involved, it's argued that the real parts of the terms contributing to Pew and Puer have specific signs. Text wrangle Langle and text wrangle down found to be positive.
What does this positivity imply for Pew dollar and $3?
It leads to the conclusion that Pew must be negative. This means the Hopf bifurcation itself is supercritical. The amplitude of oscillations grows smoothly from 0. More importantly, the analysis shows that the coefficient $, which involves the term P, epsilon, d omega 2 no, EQ192, is always positive, because P is positive.
Okay, so the crucial result for the bimodal example is Pew dollars and $3 the Zeller. What does this combination predict for the stability of the waves?
Let's check the stability conditions from the normal form analysis, often shown in diagrams like Figure 2. For standing waves, where 60 imparts are up to $2 CO, since Pew dollars and R2, both conditions are met. Therefore, standing waves are supercritical and stable.
And for traveling waves, where one amplitude is $6, the other is 0.
Stability requires Pew H dollars, which is true, and the Allers Lars, but we found over college is positive. Therefore, the second condition fails. Traveling waves are supercritical.